Thank you, Jyoti, for the introduction. It's rare that I give a talk like this outside my comfort zone, but I am not a medic, and I'm in awe of all the work that you guys do. So what I'll try and do here is to give you a bird's eye view of the work that we do, but also towards the end, try and look at some implications for the work that I'm doing in the context of your field. Just as Jyoti mentioned, one quick slide about where I come from. So I direct the Edinburgh Centre for Robotics. I'm one of the founding directors, but I also have a recent role as the program director for artificial intelligence and robotics at the Alan Turing Institute. And the Alan Turing Institute is UK's national centre for AI and data science. And we also deal, at the Institute, we also deal with lots of aspects of ethics, data security, things like how do we deal with sensitive data like the NHS in deploying some of these technologies. So it's not just about technology push, it's about looking at what is required in today's world and how do we address those challenges. So robotics, as Jyoti mentioned, is starting to affect different parts of our lives. So from the very traditional areas like we've seen sort of car manufacturing, et cetera, to being part of significant number of surgical interventions. You've seen the Da Vinci and many of the other machines that you see just next door, helping surgeons and clinical colleagues to actually deliver services that are, first of all, much more reliable, maybe potentially easier on the sort of concentration aspect of things, and take away some of the more mundane things if there is something like that in neurosurgery. So today I'm not going to talk to you about the Da Vinci machine, or I'm not going to talk to you about the robots that are used to improve surgery, because hopefully you guys know all about it, because when I'm on the operating table, I expect that you are experts in this area. But what I do want to talk about today is something what I call shared autonomy, where the idea is not about pure teleoperation or purely autonomous behaviors, but somewhere in between. So this is what this slide sort of reflects. So the two extremes of teleoperating a robot to exactly mimic surgeons' sort of say actions versus a lot of research going into fully autonomous behaviors, whether it's in robotics or in surgical systems. But really the sort of sweet spot is somewhere in between, where we're looking at what we call shared autonomy. And why do I believe that is important? Is because, I mean, this quote is very interesting, because it's like saying, full autonomy is a 20th century rhetoric. The real frontier is collaboration, which involves, I mean, this is the key, different levels of autonomy at different moments. So effectively, systems that are able to turn on autonomy when it's useful, but still have humans in the loop and be in charge, in control of things that we want to address. And again, this is important because we need to use robotics not just in the surgical field, but in areas like inspection, repair, and maintenance, for redeployment in sort of emergency situations, for things like exoskeletons, and I'll show you a few examples of the work that we do in this space. But what you see here in the slide are the different areas that our group works on in robotics. So what I want to do to begin with is to give you a broad overview of this notion of shared autonomy, where the two extremes of autonomous behaviors and teleoperations come together in operations that may or may not be relevant for the medical field, but you'll see the analogies there. So let me start by giving you an example of some robots that we use in extreme environments. So extreme environments like offshore oil and gas platforms, nuclear industries, deep underwater mines, etc. So we work with robots like these. So bipedal robots, wheeled robots, quadruped robots. And the challenge of working with these robots is just like you might have seen with medical robots, the idea is we need to be able to plan, sense, and complete the loop in a closed loop fashion in extremely challenging environments. So in this case, here's a robot, a quadruped robot, trying to climb steps on an offshore oil and gas platform. And working in very challenging environments like slippery surfaces. So if you think about it, the idea, the concept is that you want to be able to operate a device from either the next room or the next city or maybe even a different planet. So while significantly devolving the local decisions to the robot, while the human, or the surgeon in this case, are making some high-level decisions about path planning, about wire points, about scenarios that may involve some delays, but the local operations are being done on site. So here's a tool-armed robot clearing debris. So in this case, the operator uses this little window there to just say, pick this up and put it here. But everything else is autonomous, including mapping the environment, sensing what are the obstacles in real time, navigating, and deciding for itself how to clear the debris and move around. So you can think about an analogy in brachioscopy or any other kind of surgery where the surgeon decides how to operate and what are the parameters to operate in, and the robot helps you do that by reducing error, increasing the sort of reliability of manipulation. And this is exactly the concept of shared autonomy, where it's not the robot making decisions on its own, but the human doing the high-level decisions. Okay, so I want to talk about. So this is the general notion of sense, act, plan, and execute in a common loop. This is not new. Robotics is around for many, many years. The maths behind robotics has been around. But I want to talk about three very fundamental concepts that I think is very crucial for taking robotics to the next generation. And the first thing is this concept of what I call topology. So when we describe tasks, whether it is navigating inside the brain or having an endoscope put into through some vessels, it's very hard to represent these trajectories in classical Euclidean spaces. So we need a notion of topology to understand the relational relations between the end effector and the objects. So here's an example, a very simple example of a robot arm, a multi-degree of freedom robot arm reaching into a box. We can do it in many different ways, but if we use a concept of topology, then when the box moves, the concept of what is inside and outside the box moves with it. So by using topological constructs, what we can do is be able to replan, adapt, change the behavior of the robot on the fly without having to do explicit replanning. And this is very, very relevant for structures inside the human body that you plan with a static image, but during operations, things move, things you use fiducials to figure out how the movements happen. So these concepts are extremely important for understanding this. So this is, again, applying topology in a scenario where a robot has to climb a very complex structure. So again, you see real-time sensing with topology in terms of steppable areas and being able to plan, close the loop, and adapt on the fly. So here's a visualization of what the robot sees from the sensing information, building this map on the fly, and being able to navigate this terrain. So this is not, the important thing is this is not offline planning. It is planning that is happening in real time, and the navigation happens in real time. So you can see the implications of this in your field as well. The second concept I want to talk about is dealing with uncertainty. robots of today, including the robots that you use for many of the operations, including the Da Vinci and other machines, the intuitive surgicals, etc., they are rigid systems. So systems that have some built-in compliance, but they are inherently working in very structured environments. If somebody bumps into it, or you know, if there is an obstruction, then it will either freeze or say, you know, correct itself. So the idea with uncertainty is that even if you have the best planning algorithm, even if you have the best control system, the world is inherently stochastic. And the idea is, if you need to deal with this real-world situation, then you need to build systems that are inherently compliant, just like humans are. So when we walk around and somebody bumps into you, you give in while trying to maintain the key kind of parameters. And this is exactly what we want to try and do with compliant actuation systems. So we've done a lot of work in building compliant actuation systems. And last but not the least, we want systems that, within a certain limit, are able to learn and adapt. So I'll give you a very sort of toyish example of this learning process. So here's a robot arm on the left doing what typically a baby does, what we call motor babbling. So basically applying random forces to the robot arm and collecting that data and storing that data and using a learning process to understand the relationship between the forces that you're applying and the consequences of your action. So once that kind of relationship has been acquired with data and learned, then you can do something very fancy. You can do things like, you can, instead of programming a robot to do a task like balancing a pole, you can use a concept called reinforcement learning to get the robot to learn how to do a task that you want it to do. So in this case, it has multiple trials, and it basically figures out that the different actions at different state spaces results in success or failure, and eventually it detects, it finds the right set of parameters and right policy to balance this pole. And why is this important? You can do this with classical control as well, but why this is important is if I now change the stick from from that to a shorter or a longer stick, or if I change the weight of the stick or the distribution of the weight, then by using real-time adaptation and data, it can adapt to the situation. So these are the sort of three ingredients I wanted to sort of get across to you. The adaptation, the compliance for safety, and the fact that you need to work with structures or relationships that are, you know, much more built for interaction. Okay, so what I want to do next is to give you a few examples and finish with some examples relevant to the medical field. But as Jyoti mentioned, one of our flagship projects is working with NASA on the pre-deployment missions, which means effectively deploying humanoid robots for maintenance of space station on the ISS, ultimately on moon base, as well as the Mars missions. So here's a quick video of the robot coming to us 6 years ago.
Now meet Valkyrie. It's a NASA robot worth over £1.5 million, which has just been delivered to researchers at Edinburgh University. Their task, to program it to act like a human so it can carry out space exploration that's just too dangerous for astronauts. Our science reporter Victoria Gill has had exclusive access to the robot and the team.
Yeah, we'll let you know when we get ready for the download.
250 miles above the planet, the International Space Station has been home to more than 200 astronauts and one robonaut. But the next generation of this type of robot is being developed back on planet Earth, and it makes this one look quite retro.
You are looking through the eyes of a very human-like robot. This is Valkyrie. It's NASA's 6-foot humanoid. It's designed to work in disaster zones and even go to space. But it's just arrived here at the Edinburgh Centre for Robotics so that programmers here can push the boundaries of how humans and robots work together.
Worth in excess of £1.5 million, with 44 movable joints, scanning lasers and cameras to simulate human vision, this is NASA's most advanced humanoid.
Valkyrie is an amazing and unique piece of hardware because there are only 3 of its kind in the world.
But the team here has to create a set of instructions that will allow this robot to understand how to use its body.
It's going to move the arm.
To carry out every new task.
You need to make it do the things that we take for granted. For you and me, for walking, balancing, dexterous manipulation, it comes to us naturally. For getting a robot to do something like that takes a lot of effort.
With a core set of human skills, Valkyrie could be put to work in unpredictable environments.
I'd like it to be able to do very benign things, everyday actions, to be able to do what a human being does, to be able to mitigate situations that happen sometimes in a disaster relief, for example Fukushima, to be able to do maintenance on the International Space Station is what NASA are interested in.
It's hoped that humanoids like Valkyrie could be sent ahead of human astronauts to explore the surface of Mars. But this very young robot is still learning. It takes several attempts to master every new skill. The ability to control its balance and motion, though, could have an impact much closer to home.
Doing research on a human-like robot, that can nicely feed into technologies that are very relevant socially. So, for example, some of the work on exoskeletons for support of human disabilities, things like prosthetics for people who have lost a limb.
The ambition for Valkyrie's future is beyond this planet. But this work could also lead to technologies that could change and even save human lives. Victoria Gill, BBC News, Edinburgh.
So you can see here, this is 5 years ago. We've done some progress with the robot since, and we've had a second humanoid platform. But the idea is, the concept is going away from classical robotics, like fixed jig systems, robots and humans working side by side but not together, to systems that work collaboratively. And this is the trend that you're seeing in your field as well, where it's not about the robot and the human or the surgeon working independently but working closely together. And this is the kind of technology that we want to kind of further develop. And this is another quick example of the progress since, in terms of locomotion, in this case on uneven terrain, using real-time sensing, closed-loop, onboard compute to do a navigation on an uneven terrain, which is extremely challenging for a bipedal robot like this. Now I want to switch very briefly towards the end to some work that we're doing in the space of adaptive assistive robotics. So in upper limb prosthetics and lower limb prosthesis, because I think some of you here might be working in this space as well. So one of the things that we've been working on is use of exoskeletons like these. So upper limb exoskeletons with FES, so functional electrical stimulation. So combining 3 agents, the residual muscles of a human who is either, has some sort of disability. I'll just play that again. With functional electrical stimulation and exoskeleton assistance. So this is what we call a triadic collaboration, where we want to try and get all of these 3 agents working in harmony to assist a person to walk, to help with rehabilitation, etc. We also have some exciting work on upper limb prosthesis that we've been working with the NHS on EMG and IMU-based pre-shaping of grasps. So in this case, this is some real-time testing with amputees on pre-shaping of the grasp so that the cognitive load on the person is reduced. So we attach, in this case, an IMU and EMG sensor on the residual part of the limb, and for different tasks, by learning, you can pre-shape the behavior based on the task that the person wants to carry out, and that helps by reducing the cognitive load in terms of controlling such systems. And it's a similar thing with contralateral. So in this case, you've got some contralateral activation on the hand that is sort of transferred to this control of the prosthetic limb on the right hand. So this concept of triadic collaboration, right, it could be generalized to many, many different things. So it's about assisted living in healthcare, with rehabilitation, with industrial workers. So it's about trying to think about how we make sure the classical physical-human interaction and the human-robot teaming work comes together for this kind of triadic interactions. And the way we do that is a recent white paper that we published at the Royal Society, is to think about this as an optimization problem. So you can naturally set this as an optimization problem where you say the ergonomic risk for a human agent helping a patient is about patient safety, but also about the carer safety. So if we take that kind of approach and translate that into a formal mechanism, you get a very nice optimization framework in which you can work. So all of this work in terms of predictive modeling, ergonomic metrics, and real-time controllers can kind of come together. So recently, I don't have that slide here because this is still stuff that we're working on. So we've been working with the Anne Rowling Clinic at the Edinburgh University on looking at this kind of triadic interaction. So FES-based activation for reducing spasticity, as well as helping with drop foot for MS and MND patients, working with them to sort of, first of all, analyze the data so that we can look at things like gait data to be more stratified for example, if you have an EDSS scale for comparing the progression of the disease for trials, then we can use much more sophisticated AI to understand the exact stratification, and then sort of close the loop with the right intervention. Could be with FES, could be with PES, it could be with exoskeletons. So again, I'm not going to go into the details in the interest of time, but there are two kind of case studies we are currently working on. One is assisted living, so exoskeletons for assisted living for the carer, and the second one is the one that I just talked about, the rehabilitation setting, where the agents include the patient, the exoskeleton, and the FES. So the FES, obviously, the functional electrical stimulation, we all know if you use it extensively, people get tired, and there is a fatigue aspect. So it's about doing assistance as needed while the patient is still encouraged to do the motion, and the exoskeleton kicks in when the fatigue sets in. So it's about automatically modeling this and switching between these things. And these insights we are getting because we've done a lot of work with robotic systems, with bipedal robotic systems, so that we can translate some of that insights into human exoskeleton work. Okay, I'm nearly going to conclude here. So the future of work. So we've seen, I don't know how many of you recognize this. This is from one of my favorite movies. This is the Iron Man, and it's Tony Stark trying to control various agents from his, the comfort of his home or office. So this is not very far away. So we recently deployed some of these techniques in a cafe in Japan. This is a robot barista cafe with teleoperation, with shared autonomy, where the robot does a lot of work autonomously. But what you don't see in this picture, and you might hear some voices, is this is semi-autonomously teleoperated by a patient in another city. In this case, this is Tokyo, another city in Osaka, and some people in Sapporo who are stroke patients, who are one of them is completely paralyzed from neck down, other one is paralyzed from the hip down. So this is trying to get people who are in such situations into work, giving them a sort of a way of earning a living by combining this teleoperation setting with the autonomous behaviors, safe autonomous behaviors in a cafe barista setting. So this is actually, if you now go to Tokyo, you can actually go to a cafe, get a coffee and a tea made by this robot, which is remotely operated by the people who normally would be out of work. Okay, just finishing up. So what are underlying sort of open scientific challenges? So I still think there is a lot of work to be done in terms of safe actuation, and even if we are applying it in surgical, especially when in the healthcare settings, safe actuation, safety is extremely important. You've seen the use of what we call digital twins in a lot of our work. So this will help us understand a lot of the limitations and challenges by doing a lot of work offline in simulation. But also, one of the other challenges is to build systems that are verifiable and explainable. So if something goes wrong, can we understand what went wrong and how to fix it so that it doesn't happen again? What I didn't get a chance to talk about are some of the other questions that we need to address in terms when we apply robotic technologies, things like bias in data, security of data that's being collected, responsibility and explainability, transferring control, learning systems. So these are all interesting questions that we still are in the process of addressing, and the Alan Turing Institute, for example, in my role, addresses some of these questions in conjunction with people like the NHS for the data aspect. So I'm going to conclude here with a little video which shows the summary of the work that we do, but also highlights the people behind the work. So all the people, my postdocs, PhD students, some of the collaborators who've done this excellent work. So I'm going to finish with this video here. Welcome to the Statistical Machine Learning and Motor Control group at the University of Edinburgh. Here we do exciting, world-leading research on robotics, machine learning, and data-driven techniques using artificial intelligence to make robots a lot more versatile and adaptive to the real-world situations. We do work across domains, so applying the core problems in robotics and machine learning to domains in oil and gas, transport, healthcare, as well as things like the challenges of exploration in outer space.
We want our robots to be autonomously deployed in industrial plants, for instance, to perform inspection tasks, to accomplish tasks that humans can't do or that are dangerous for them.
Our main business is to educate the next generation of outstanding postgraduate students and conduct cutting-edge research.
My research is focused on designing exoskeleton controllers that can assist people completing tasks such as walking. And to achieve this, what we do is we build quite complex neuromuscular models of human subjects and combine this with a very detailed set of motion data that we can collect in our gait lab.
We hope that with this setup and combining robotic assistance with electrical stimulation, physical therapists can have a tool to personalize the intervention and improve the outcomes of physical therapy.
My research is about robot localization in changing environments, when the robot's view is nearly occluded by large moving objects.
We want the robot to learn which objects are of interest without requiring a human to provide information about the shape or the visual appearance of these objects.
In order to enable robots to move while in contact, for example, when wiping a table or pushing a heavy object, my research focuses on how to plan or how to learn those types of physical contact interactions.
We are developing mathematical models to enable a robot to capture heavy and moving objects with two arms. At the same time, we are handling impact.
My research involves both humans and robots, where first we enable robots to predict humans' intentions and actions, and we also generate safe robot actions in order to help the humans reach their goal.
In construction, robots are often operated by humans in dangerous environments, needing expensive training. To reduce the operator burden, I'm working on shared autonomy, which combines human input and autonomous methods so the human can best utilize their expertise.
I'm really interested in human-robot collaboration, so how we can enable robots to perform a common task effectively with humans, such as pouring a wine into a human's glass. But humans are really difficult to predict, and so I'm interested in how we can better make those predictions.
I'm working on the development of robots that can be easily taught to manipulate objects and potentially collaborate with people or assist people in need just by giving a demonstration of the task.
I'm working on leg robots to make them traverse challenging terrains. The idea we propose is to start with a capable controller that already works on the robot and try to extend and add capabilities to make the robot cross challenging terrains.
I'm working as a software engineer in a field robotics lab, and also I'm doing some research about quadruped robots. I'm working on how those robots with 4 legs should plan their footsteps considering the torque limits on their legs.
When robots have to perform manipulation and walk simultaneously, they face a lot of uncertainty. One way we can increase the robustness of the system is by taking into account the capabilities of the robot, so its motors and also the contact stability.
There are many conditions that we cannot predict. For instance, when we are navigating in an offshore platform, we might encounter a floor that is wet. A way of dealing with this kind of uncertainties is by replanning quickly new motions.
I'm working on building better robots for specific tasks. So a robot that walks might need to be built a little differently than one that jumps. And so I'm working to create algorithms that modify the designs based on the tasks. And I'm looking at making those more efficient and physically realistic.
My work focuses on motion planning, especially when it comes to the environment changes, there are the obstacles coming in and out, or the objects that the robot is trying to pick up and move are moving. And this is especially useful when working with robots that need to be safe around people and other robots.
So the environment may have many different inclined slopes, and this gives rise to a lot of different options of when to play the foot and where to play the foot.
Robots in the real world have to operate in environments where obstacles around them are moving. So whether that's in hospitals where we have people moving around, or whether that's in a factory where you have other robots that you might need to avoid. My research interests are in developing algorithms and motion planning software that will allow us to move robots in ways that avoid those obstacles.
I've particularly enjoyed working on the large-scale projects which we have within the group, and helping with the project management side with the Alan Turing Institute, the ISCF hubs, and also the EU Horizon 2020 projects.
So if you've liked some of the research that you've seen in the video and would like to work on some of these exciting platforms and projects, please do get in touch with us, and we'd love to have you as part of our team. Thank you very much.
So I think we are just a couple of minutes over time. I'll take the opportunity to thank you again, and we'll have to stand in the right spot or we get rolled up.
Okay.
In terms of shared autonomy, any shared autonomy questions? Any questions from the audience? One in the back for Prof. We'll take one question and then we'll move on.
Thank you.
Thank you very much for your talk. I'm a neurosurgery trainee in the Southwest. It was really kind of beyond the laws of Isaac Asimov and the principles of robotics there. What codes of conduct do you use as researchers, and what do you put into your robots to conduct themselves autonomously in a good way?
Yeah, so I think there are two aspects to your question. One is what can we predict? Because when we have learning systems, the input-output function is constantly changing. So we need to put in some bounds in terms of these learning systems. So that's the first aspect. And the second aspect is how can we make them inherently safe? So going back to your question of do no harm. And so that is what I mentioned in the sort of third of my, or the second of the topics there, which is about building an inherent compliance, which means that even if the software fails or something catastrophic happens, the robot, even though it's heavy, is giving in or is compliant. So it is, by design, supposed to be more safe for interaction. So those are the two things that we kind of use as a fail-safe for addressing your problem. Excellent. Thank you very much.
Thank you very much.